Let's have a look at where emissions are coming from and where emissions are going to. And in order to do so, I'm going to use the Kaya identity. Kaya identity is given here. It has that emissions E are equal to the number of people, P, the size of the population, times per capita income. This is total income, this is the size of the population, so this is per capita income, times the energy intensity of the economy. X is total primary energy use. Y is the size of the economy, so this is energy intensity of the economy, times the emission intensity of the energy sector or the energy supply. So E is emissions and X is total energy supply. Now this is an identity. P cancels against P, Y cancels against Y, X cancels against X. And what we have is that E equals E. So this is true. As that's why it's called an identity. Now, this identity is not only true, it's also useful. And you can use it to understand where have emissions come from, why have emissions gone up, and what would we need to do to bring them down in the future. What you're looking at here are total global carbon dioxide emissions from fossil fuel combustion from 1970 to the year 2018. That's the most recent year for which all data are available. And in black, you're looking at the CO2 emissions, and it's indexed so that 1970 is 1. And what you see is that over this almost 50-year period, emissions have more than doubled. They've gone up by 125%. So you may wonder, how come? Now, that's where the Kaya identity comes into play. The first term in the Kaya identity is population P, and that's the red line that you see here. Now, what you note is that over this 50-year period, almost 50-year period, the world population has slightly more than doubled. It's gone up by 102, 103%. So that is the first driving factor. There's more people, and therefore there is more CO2 being emitted. Actually, what you see is that CO2 emissions have risen faster than the number of people. So per capita CO2 emissions have gone up. The second element of Kaya identity is GDP per capita. How much money we make, and that is given here in the blue line, and you see that has also more than doubled over this almost 50-year period. CO2 emissions actually have increased slightly faster than per capita income. Now, the total size of the economy is, of course, income per capita times the number of people. If population has doubled, income per capita has slightly more than doubled. That means that the total economy has grown by a factor 4.5. CO2 emissions have only grown by a factor 2.25, which means that the CO2 intensity of the economy, the amount of CO2 emitted per dollar value added, has actually fallen over this 50-year period. And the question is, how come? Well, that's where the third and the fourth element of the Kaya identity come into play. In purple, you're looking at the energy intensity of the economy. This is how much energy we use per dollar value added. And over this 50-year period, that has almost halved from 1 to slightly above 0.5. Which is a quite substantial improvement. The final component of the Kaya identity, carbon intensity, that is how much CO2 do we emit per unit of energy used, has barely changed. It started here, it went up a little bit as we started using more oil, then it went down a little bit as we started using a little bit more gas, and then it went up again as the coal-rich economies of India and China started growing. And then in the most recent years, it has come down a little bit again. but over the 50-year period it has barely moved. All the hype about renewables has barely made a dent in the carbon intensity of the energy supply. So the Kaya identity is useful in understanding, in decomposing trends in emissions in the past. This gives you a rough idea of why are emissions going up as much as they are. Now, having done this for the past, we can do this for the future. That's where a graph like these comes from. So we're looking here at the global mean surface air temperature as observed over the previous century and as projected over the current century. Actually, it's a slightly older graph. 2007, it's 13 years old now. The areas that you see indicate the uncertainty about the climate models. Climate models are far from perfect. The alternative colored lines that you see are alternative ways in which the future might unfold. And the way that these scenarios are constructed is essentially extrapolations from the Kaya identity. So here we have the Kaya identity again, and then you see Yotzi displayed, Yotzi Kaya, who first came up with this identity. If you want to know what future climate change will be, then you will need to know what future emissions will be. Because climate change is driven by the concentration of greenhouse gases in the atmosphere, and the concentration of greenhouse gases in the atmosphere is driven by the emissions of greenhouse gases. So if you want to know what the weather and what the climate will be like in the year 2100, you need to project what emissions of greenhouse gases will be between now and the year 2100. And the Kaya identity actually helps to do that and tells you something about how difficult this will be, right? Because if you want to know how much CO2 will be emitted in the year 2090, then you need to know how many people there will be, how rich these people will be, how much energy they will use, and what sort of energy they will use. And as soon as you know that, you know what emissions will be. CO2 is not the only greenhouse gas. We also talked about methane. Methane mostly comes from waste and food production. So you will also need to project how much waste people will generate in 100 years' time, how much food they will eat, what sort of food they will eat, how that food will be produced, and so on and so forth, in order to project methane emissions into the future. And this particular exercise is difficult. It's more daunting than it even seems. But it's the only way to do it. And a number of brave, some say foolish people have indeed done this. Here we're looking at 5 sets of recent scenarios developed on behalf of the Intergovernmental Panel on Climate Change. And they're called the Shared Socioeconomic Pathways, or SSP. And there are 5 of them, and they're imaginatively called SSP 1, 2, 3, 4, and 5. And these scenarios here are split by the Kaya identity. So here we have population, here we have per capita income, here we have energy intensity, here we have carbon intensity, and if you then multiply all this, you have your emission scenarios. Let's start with population. What you see is that there's essentially only 3 scenarios. Also what you see is that there's very little model disagreement. So the central line is the average across a number of models, and then the dotted lines that you actually barely see is the disagreement or an indicator of the disagreement between the models. That's not because projecting population is so easy, but it's more because the models tend not to focus on this and just clone each other. And what you see is that there's 3 alternative scenarios. So this is the past, and then in some scenarios population peaks at 8.5 billion. In other scenarios it peaks at 9.5, and sort of stabilizes in the first set of scenarios it goes down, and in this scenario it actually continues to grow up to 13 billion people. There's now roughly 7.5 billion people on the planet. So these are very, very different futures. Now you may wonder, how come projecting population is easy? Well, that's not true. The first question is, how many people are there currently on the planet? And many countries actually do not have a proper population register, so it's actually a bit unclear how many people there are on the planet now. There are some websites that will tell you to 9 significant digits how many people there are, but that's just a lie. We don't really know how many people there are currently. You may think that, well, that's the smallest problem. If we start projecting people into the future, that is relatively simple, because essentially people are born, they have a certain chance of making it to a childbearing age, they will have children, and then they have a certain probability of making it to 90 or 100 years old, right? That is statistical regularities, and that is to a degree true. It's safe to predict if you have a class of 20-year-old students, and in 15 years time the vast majority of those kids will be fathers and mothers. That is a fairly safe prediction, but the big uncertainty is how many children will mothers have over their lifetime. The central scenario here used to be the best guess, but then later on it was revised to this scenario here, and the big difference was that this particular scenario was based on the trend in fertility in Africa between the year 1990 and the year 2000. And during that decade, fertility across Africa fell very, very rapidly. Demographers got all excited and extrapolated that into the future for a century or so. And if you do so, then you end up with this particular line. The trend between 1990 and the year 2000 actually was an aberration of the long-term historical trends. And if you look at trends in fertility between 1950 and the year 2000, you actually end up here. And unfortunately for demographers, after the year 2000, fertility sort of reverted back to its long-term historical trend. That is, women get fewer and fewer children, but only that decreases only very slowly. And that is the difference between these two. And the difference is 3.5 billion people. That's actually 3.5 billion people born in Africa. Recent demographic work is pushing this line downwards again, but it hasn't penetrated the climate community yet. So that is population, and that is just hard enough to do, albeit a relatively simple problem. For anybody who's done anything with growth theory or macro or whatever it's called nowadays, predicting how the economy grows is actually difficult too, but it needs to be done over a century or so. Here we're looking at 5 alternative scenarios of what the world average income would be. You immediately see a disconnect here. Even though we have 5 income scenarios, we only have 3 population scenarios, which suggests that fertility and mortality is not related to per capita income, according to the people who made these scenarios. Of course, it is in reality, but not in the models that generated these pictures. Current income for the world average stands at around $7,000 per person per year. In the most pessimistic scenario, that goes up to 20,000. They are roughly talking about Portugal or so. That's relatively well-to-do, and that's the most pessimistic scenario. The most optimistic scenario, per capita income at the end of the century goes up to $135,000 per person per year. That's the average. That is richer than the current richest country on the planet. This is Luxembourg, which has a per capita income of $110 per person per year. So if this scenario comes true, the average person on the planet will be richer than the average person in Luxembourg at the moment. So that is a fairly rosy picture if you believe that material well-being matters. It's very hard to imagine that that would be the average income. If income inequalities continue roughly as they are today, then there will also be countries that have an average income of $500,000 per year. It is hard to imagine what that world would be like. But then again, if you put yourself 100 years into the past, we are incredibly wealthy compared to the people in 1920. And the people in 1920 could not imagine what our life would be like given our income. That's simply beyond their comprehension. So maybe $135,000 per person per year sounds a lot, but maybe that's what's going to happen. Another thing I want to say about this graph is that all the lines are going up. The most pessimistic scenario sees that the per capita income more than doubles in 8 years' time, which seems optimistic for the most pessimistic scenario. The reason for this is that these scenarios essentially come out of a United Nations process, and there needs to be, in this particular round, there needed to be tacit approval of all the countries in the world. So no country, apart from the United Kingdom, no country consciously plans to shrink its economy. No government would do that, apart from the Boris Johnson government. And therefore, if you present scenarios to the United Nations, you can only, if you want approval of the member states, you can only predict economic growth. And that is why this most pessimistic scenario is in fact fairly optimistic, or it's a good scenario. There's no economic stagnation, there's no economic decline on the horizon if we believe this set of scenarios. So that is population and per capita income. Here we're looking at energy intensity. How much energy do we need to make a dollar worth of value added? We see history here. It's dropped, and then a sort of a slight dampening out of the drop. But when the scenarios take over, then the longer trend continues, and we see a drop in energy intensity. These scenarios are roughly in line with the observations, not just over the 50-year period that I showed you before, but also over much longer periods for selected countries and selected indicators where we have this data. So that seems to be reasonable. Of course, there's a range there. Some scenarios are fairly pessimistic. There's a 20% drop or so, 25% drop in energy intensity, and others are fairly optimistic. See energy intensity drop by almost a factor 4, which seems to be in line with history and also what is physically possible. Final graph, and that is where the models really start to disagree with each other, is the carbon intensity. What energy do we use? Do we continue to use coal? and oil and gas, or do we switch to renewables? Again, the black line is history, and then the colored lines are the scenarios, the models taking over. You see an enormous range, an enormous disagreement between models. This is where the modelers really are going to tell. You also see they actually could not quite agree on what happened in the year 2010. Same here, but more pronounced here. Which is more of a worry. The fact that models disagree about the future is a good thing, because we don't know the future. You want model disagreement about predictions, otherwise there's really something wrong. But you would hope then everybody has the same past. But it didn't. You see here that the most pessimistic scenario essentially keeps the carbon intensity as it is. The most optimistic scenario sees it dropping, that is, a switch away from coal towards gas and towards renewables and nuclear. When that happens and the carbon intensity comes down, if we sort of keep the energy mix as it is today, then it won't. Keeping the energy mix as it is today is actually going to be hard because we are running out of all sorts of stuff, gas and oil, conventional oil. So it's hard to imagine that we will keep the energy mix as it is today, but one of the scenario models managed to do exactly that. The increases that you see here, one of the models says, no, the CO2 intensity is going up. That means that if we are running out of oil and gas, which we are, then we're not going to replace that oil and gas with renewables and nuclear, but instead we're returning to coal. Now that is easy to imagine technically. In power generation, it's harder to imagine for most people if it comes to driving your car, right? But there are chemical processes to liquefy coal. There's also chemical processes to gasify coal. So technically there's absolutely no problem why we would not be switching back to coal, and there's plenty of coal around. The issue with this scenario that makes it, I think, less than plausible is that we're running out of cheap coal. We basically dug all the cheap coal out of the ground. There's more left in Australia and places, but that is coming to an end. But if we're really going to use all the coal that is in this scenario, then you need to start digging for coal that is there. That's not the issue. It's physically there. But that is very deep coal, or coal in places like Antarctica that is very hard to reach. And that means that it will be very expensive to mine. And saying, oh, that's what we're going to do is hard to imagine if you've looked at the price of wind and solar power. It is very hard. At the moment, coal has difficulty competing. It's hard to imagine that more expensive coal will be able to compete with, according to all projections, cheaper wind and solar. And that makes, I think, this particular scenario fairly implausible.